Good morning, student. Welcome to TYBSc Organic Chemistry. I am Dr. Kailas Labhade, Associate Professor and Head, Department of Chemistry, S.V.K.T College, Devdali Camp, Nasik. Student, today we are going to see ultraviolet and visible spectroscopy. In this session, we are going to see what is UV and what is visible spectroscopy. We are going to see the instrumentation of spectrophotometer. Then we are going to see electronic transition or electronic excitation. We are going to see different terms used in UV spectroscopy, that is chromophore, oxychrome, pathogramic shift, hypsochromic shift, and finally we are going to see isolated and conjugated dynes. At the end of this lecture, students should understand the basic principle of UV spectroscopy. They should be able to understand what is electronic excitation or electronic transition. They should be able to understand the terms chromophore, oxychrome, pathogramic shift, hypsochromic shift, hyperchromic shift, hypochromic shift, etc. And they should be able to differentiate isolated and conjugated dyne on the basis of their knowledge of UV spectroscopy. Ultraviolet spectroscopy is the spectroscopy which is used to find out the conjugation present in the molecule or compound. It is also used to find out presence of double bond, presence of triple bond, or presence of ring system in the molecule. It can be used to differentiate conjugate and isolated dynes. It is used to differentiate carbonyl compound from alpha beta unsaturated carbonyl compound. It also gives idea about the stereochemistry of the molecule. Both UV and visible spectra have basic of electronic excitation, or they based on electronic excitation. When electron gain energy, they excited from lower energy level to higher energy level. The energy is supplied in the form of light. As energy level of molecules are quantized, the amount of energy required for promotion of electron from lower energy level to higher energy level is fixed. Let's see electromagnetic radiation. Ultraviolet spectroscopy is in the region from 200 to 400 nanometer, and we know that region of visible spectroscopy is from 400 to 800 nanometer. There is another term that is called vacuum ultraviolet. It is from 15 nanometer to 200 nanometer. Vacuum ultraviolet means UV spectroscopy cannot be used below 200 nanometer, as radiations are absorbed by air due to presence of moisture and also due to the electronic transitions of atmospheric oxygen, nitrogen, and carbon dioxide. There are various gases in atmosphere, and in that gases electronic transition or electronic excitation is possible. In order to study the transition below 200 nanometer, that is from 15 to 200 nanometer, one must use vacuum apparatus, and this region is called as vacuum region. Now the spectrophotometer. Spectrophotometer is the instrument which is used to get spectrum, that is UV spectrum or visible spectrum, and this is the diagram which shows different component of the spectrophotometer. There is light source, generally deuterium or tungsten lamp, that can be used as a light source. Then there is monochromator, prism or diffraction grating, that can be used as a monochromator. Slit is for controlling incoming radiation. There is sample holder is generally cuvette. It is made up of silica or quartz. There is another cuvette that containing solvent only, one cuvette containing sample. there is detector, photovoltaic cell or photomultiplier tubes can be used as a detector, and finally there is readout device, and we can get the spectrum of that molecule by using this spectrophotometer. Spectrophotometer is the instrument to get the spectrum, that is UV spectrum or visible spectrum of the molecule. Now, source of the spectrophotometer, as I already mentioned, that deuterium or hydrogen discharge lamp that can be used as a source. It can be used from 180 nanometer to 400 nanometer wavelength, and tungsten lamp, if we want to use tungsten lamp, it can be used above 375 nanometer. Sample container is the cuvette, and it is made up of quartz or fused silica. Generally, inner diameter of that cuvette is kept 1 centimeter. Then sample and solvent, few milligram of this sample that is dissolved in 100 ml of non-absorbing solvent, just like cyclohexane, 1,4-dioxane, water or 95% ethyl alcohol. One should use the solvent which is non-absorbing, and that is very important. If we use the solvent which shows the absorption in UV region, then error is going to arise in our determination. That's why solvent use should not non-absorbing solvent. Now, Beer-Lamberts law. In analytical chemistry, we have already seen what is Beer's law and what is Lamberts law. We have also seen combined Beer's-Lambert law. According to Lamberts law, intensity of incident radiation, that is decrease in intensity of incident radiation, is directly proportional to the path length of the cell. According to Beer's law, decrease in intensity of incident radiation is directly proportional to the concentration of the solution or the molecule which are present in the path length of the solution. And according to Lamberts-Beer's law, both of these laws, they are combined to form Lambert-Beer law, and it is stated like this: when a beam of monochromatic light is passed through a solution containing absorbing species, the decrease in intensity of light with path length is proportional to the concentration of the solution and the intensity of incident light. Hence, decrease in intensity is based on or depend on the path length of the light as well as the concentration of the solution, and this is called Beer-Lambert law. Let's see this diagram. Here, source of light is shown, incident radiation which having intensity I0. When it is passed through the sample, that sample is kept in cuvette, and L is the inner diameter of that cuvette. I is the transmitted light. Some of the light may absorb, some of light may reflected, and because of that transmitted light is reduced. When incident light strike on the sample kept in cuvette, part of it absorbed and remaining part is transmitted. And this is the equation which shows relationship between absorbance and incident as well as transmitted light. A is equal to log of I0 divided by I. A is equal to epsilon BC, where I0 is the intensity of incident light, I is intensity of transmitted light, A is absorbance, epsilon is extinction coefficient. It is also called molar absorptivity. B is path length. Sometime B is replaced by L. B is path length of cell in centimeter, and C is the concentration of the solution in moles per liter. Now, very important part of this UV spectroscopy is electronic excitation or electronic transition. First, understand what is electronic excitation. Electronic excitation means promotion of the electron from ground state molecular orbital to higher energy excited state orbital. That is called electronic excitation. We know that there are three types of molecular orbital. bonding molecular orbital, that is sigma and pi, non-bonding n, and anti-bonding sigma star and pi star. When electron gain energy, they transmit it themselves from lower energy orbital to higher energy orbital, and that is called as electronic excitation. This diagram shows how that electronic excitation is going to take place, and it also shows the energy required for various electronic excitation. In this case, sigma to sigma star transition require maximum energy, then pi to pi star, n to sigma star, and n to pi star. These are other transition which are going to take place. Means the electron which are present in bonding molecular orbital or non-bonding molecular orbital, they are going to promote, or they are promoted to higher energy antibonding molecular orbital, that is pi star and sigma star. Now, type of electronic excitation. As we have already seen, there are 4 types of electronic excitation. We are going to see one by one. First is sigma to sigma star transition. In sigma to sigma star transition, promotion of electron from bonding sigma molecular orbital to anti-bonding sigma star molecular orbital is taking place, and this transition require high energy. As we have already seen in that diagram, maximum energy is required for sigma to sigma star transition. Example, methane, ethane. In this case, sigma to sigma star transition is possible, and this diagram shows how that transition is taking place. Another transition is pi to pi star transition. Promotion of electron from bonding pi orbital to antibonding pi star orbital, that is called pi to pi star transition. Molecule containing multiple bond undergo this type of transition. If your compound containing double bond or triple bond, in that case, this pi to pi star transition is possible. For example, alkenes, alkynes, carbonyl compound, all these compound can show pi to pi star transition, and in this figure it is shown how that pi to pi star transition is taking place. Next transition is n to sigma star transition. Electrons which are present in n, that is non-bonding molecular orbital, is transmitted to antibonding sigma star orbital. Compound containing non-bonding electron pair present on heteroatom, that shows this type of transition. For example, compound containing nitrogen, compound containing oxygen, compound containing sulfur, all these compound having unpair electron or lone pair of electron present on that heteroatom, and in this compound this n to sigma star transition is possible. Let's see, this is methanol, it containing oxygen, and when n to sigma star transition is taking place, there is formation of one electron is shifted from n orbital to sigma orbital, and it is shown in that figure. Fourth is n to pi star transition. This transition require minimum energy, promotion of electron from non-bonding molecular orbital n to higher energy anti-bonding molecular orbital pi star taking place. Example, acetone shows 2 absorption peak, one at 280 nanometer and other at 190 nanometer. Let's see, this is the n to pi star transition shown by the acetone molecule. Now the terms used in UV spectroscopy. First term is chromophore. Chromophore, the part of the molecule responsible for imparting color to the molecule, is called as chromophore. It is an isolated functional group capable of absorbing UV radiation. Chroma means color and phore means bearing, means the part of the molecule which is responsible for imparting color to the molecule, that is chromophore. And chromophore are the different functional group, just like N double bond O, NO2, azo group means N double bond N, C double bond O, all these are the example of the chromophore. Now another term is Oxychrome. It is the functional group which does not absorb radiation in UV region, but when they are attached to chromophore, they increase the lambda max value of that compound. These are called oxychrome. For example, OH, OCS3, NH2, these are the oxychromes, and this is the example chromophore. Benzene is the chromophore. It contains 3 carbon-carbon double bond. Lambda max value is 255 nanometer. If oxychrome is attached to that benzene ring, OH is attached to that carbon atom of the benzene ring. In that case, that lambda max value increases from 255 nanometer to 270 nanometer. If OCS3 group is attached, it is increased up to 269 nanometer, and if NH2 group is attached to chromophore benzene, then its lambda max value is 280 nanometer. Then another term that is used is bathochromic shift or red shift, and absorption to longer wavelength is called as bathochromic shift or red shift. For example, paranitrophenol shows red shift in alkaline medium. This is the paranitrophenol, and paranitrophenol, when it is treated with base, hydrogen atom of that OH group is removed by base, and there is formation of anion of paranitrophenol. This compound showing bathochromic shift or red shift. Bathochromic shift means the absorption is taking place to higher wavelength. Initial absorption at 255 nanometer in neutral medium. If you add base in that solution, means in basic medium, it is going to show the absorption at 265 nanometer. Hence, it is called bathochromic shift. This bathochromic shift is arise because of electron donating capacity of OH and O minus. They are compared. As compared to OH group, negatively charged oxygen is able to give electron more easily. That is delocalization of negative charge is more effective in second case, and because of that bathochromic shift is arise. Next term used in UV spectroscopy is hypsochromic shift. An absorption to shorter wavelength is known as hypsochromic shift or blue shift. For example, aniline shows blue shift in acidic medium. In acidic medium, lone pair of electron present on nitrogen is not available for donation. Hence, absorption taking place at a shorter wavelength. Let's see, aniline in neutral medium, lambda max value is 230 nanometer. If it is present in acidic medium, NH2 group get protonated, and lone pair of electron which is available on nitrogen is not available in second structure, and that's why in acidic medium absorption, that is lambda max value, decreases from 230 nanometer to 203 nanometer. Another term that is used in UV spectroscopy, that is hyperchromic shift and hypochromic shift. These two shifts explain the intensity of absorption. Strong intensity peak is called as hyperchromic shift, while weak intensity peak is called as hypochromic shift. For example, ethylene. Ethylene shows two peak, one at lambda max value 165 nanometer, and its intensity is 10,000. Another peak that is shown by ethylene molecule is at lambda max 210 nanometer, and its intensity is 1000. Hence, peak at 165 nanometer is strong intensity peak, and it is called as hyperchromic shift, while other is called hypochromic shift. Effect of conjugation on position of UV band. In this chapter, we are going to see two types of system. One system that containing similar chromophore, that is diene system. In diene system, carbon-carbon double bond is in conjugation with another carbon-carbon double bond, that is diene system. And we are going to see enone system. In that enone system, Carbon-carbon double bond is in conjugation with carbonyl group. When two double bonds are separated by at least 3 single bonds, then pi to pi star transition take place approximately in same region. Such dienes are called as isolated dienes. In this chapter, we are also going to see what is conjugated dienes and what is isolated diene. Conjugated dienes means the diene which containing alternate double bond single bond pattern, or two double bonds are separated by one single bond. Such diene is called as conjugated diene. In case of isolated diene, two double bonds are separated by 2 or 3 single bond. These are called as isolated diene. In this case, ethylene lambda max value is 165 nanometer, and another example 1,5-hexadiene lambda max value is 165 nanometer. Absorption wavelength of both of these compound is similar because 1,5-hexadiene is isolated diene. In that case, there is no effect of first double bond on absorption of second double bond. That's why absorption maxima appear at 165 nanometer. Now in this case, it is shown how conjugation increases the lambda max value. Ethylene, as we know that lambda max value of ethylene is 165 nanometer. Another example is 1,3-butadiene. 1,3-butadiene is the conjugated diene because two double bonds are separated by only one single bond, and its lambda max value is 220 nanometer. Hence, conjugation increases the lambda max value. Now, different chromophore means enone system. As we already discussed that in enone, alpha beta unsaturated carbon-carbon double bond is present in conjugation with the carbonyl group. Unsaturated carbonyl compound, they are called as enone system, and this is the example crotonaldehyde. Aldehyde is the functional group, and there is carbon-carbon double bond present in conjugation with that carbonyl group, and it is alpha beta unsaturated carbonyl compound, that is called as enone. Now, different diene system. In this chapter, we are going to solve some problems based on diene and enone system. In that, we are going to calculate the lambda max value of various diene system and various enone system. For that purpose, we require all these things. Acyclic conjugated diene means open chain alkene that have alternate double bond single bond pattern, that is called as acyclic conjugated diene. Homoannular diene means two double bonds are present in one ring. That system is called as homoannular diene, and these two double bonds should be in conjugation with each other. Another term that is required for calculating lambda max value, that is exocyclic double bond. Exocyclic double bond means the double bond in which one of the carbon atom is the part of the ring. In other words, the double bond which is present at the corner of the ring, that is called exocyclic double bond. Heteroannular diene means the diene in which two conjugated double bonds are not present in single ring, that is called heteroannular diene. For homoannular diene, we have to add 39 nanometer for homoannular system while solving the problem. Cis and trans diene, these are the example of cis and trans dienes. Student assignment. On the basis of today's discussion, you have to solve all these questions and send it to my Google Classroom. First question, explain the electronic transition with the help of figure. We have seen that four different types of electronic transition or electronic excitation is there. We have also seen one figure. You have to write all these things. Second question, explain the terms Oxychrome and Pathogramic Shift. We have seen different terms: Oxychrome, Pathogramic Shift, Chromophore, Then we have seen hypsochromic shift, hyperchromic shift, hypochromic shift. All these terms we have seen. You have to write down what is Oxychrome and what is Pathogramic shift. Third question, what is isolated and conjugated dyne? You have to give one example for isolated dyne and one example for conjugated dyne. Summary of today's lecture. We have seen what is UV spectroscopy. We have seen the range of UV spectroscopy. It is from 200 nanometer to 400 nanometer. From 400 nanometer to 800 nanometer, it is visible spectroscopy. And from 15 nanometer to 200 nanometer, it is vacuum ultraviolet. If you want to record the spectrum in below 200 nanometer, in that case vacuum ultraviolet is used, because atmospheric oxygen, atmospheric nitrogen, moisture, all are present, and these species also shows electronic transition below 200 nanometer. For that purpose vacuum ultraviolet is used. We have seen electronic transition. 4 types of transitions are there. Transition of the electron from bonding and non-bonding molecular orbital to higher energy antibonding molecular orbital is taking place. Then we have seen different terms that are used in spectroscopy, that is chromophore, oxychrome, bathochromic shift, hypsochromic shift. Chromophore means the functional group or the part of the molecule which is responsible for imparting color to the molecule. In another word, chromophore is an isolated functional group which is capable of absorbing UV radiation. Oxychrome is the functional group which is not able to absorb UV radiation, but when it is attached to chromophore, the absorption increases. We have seen the example, benzene, lambda max value is 255 nanometer, and if OH, that is oxychrome, is attached to that benzene ring, then its lambda max value increases up to 270 nanometer. Then we have seen bathochromic shift. Bathochromic shift means absorption to higher wavelength. Absorption to higher wavelength is called bathochromic shift. Hypsochromic shift means absorption to lower wavelength. Hyperchromic shift and hypochromic shift, that also we have discussed. Hyperchromic shift means strong intensity peak and hypochromic shift means weak intensity peak. Finally, we have seen isolated and conjugated dyne. In isolated dyne, 2 double bonds are not in conjugation with each other, and in conjugated dyne, there is alternate double bond, single bond pattern, or one double bond is in conjugation with other. Precap. In next lecture, we are going to see applications of electronic spectroscopy, and we are also going to solve some problem, that is calculation of lambda max of dyne system by using Woodward and Fisher rule. Thanks.